When you serve a large language model, every request secretly runs two very different workloads. First comes prefill. The model ingests your entire prompt in parallel, building the key value cache. That phase is compute bound. It saturates the GPU's arithmetic units. Then comes decode. The model generates the response one token at a time. Each step reading the model weights and the growing KV cache. That phase is memory bandwidth bound. The arithmetic units mostly wait on memory. Traditional deployments run both phases on the same shared hardware. That means you cannot tune either phase properly. The hardware profile that makes prefill fast is wasted on decode and vice versa. One GPU pool is serving two workloads pretending to be one. Let's make the clash concrete. Prefill processes the entire input prompt in one parallel pass to produce the initial key value cache. Its speed determines your time to first token. Decode then loops auto-regressively, producing one token per step. And every step must stream the model weights and the KV cache through memory. Its speed determines your tokens per second. Now imagine a retrieval augmented workload with huge prompts and short answers. It hammers prefill. A chat workload with short prompts and long answers hammers decode. On co-located hardware, these workloads fight each other. A heavy prefill burst stalls everyone's token generation, and long decodes hold GPUs that prefill needs. The phases have opposite hardware appetites, so co-locating them means permanently over-provisioning one of them. This is the problem llm-d attacks. llm-d is a Kubernetes native, open-source distributed inference framework, a CNCF sandbox project with contributors from Red Hat, Google, IBM, and NVIDIA. Its core pattern is disaggregated, serving prefill servers and decode servers, run as separate Kubernetes pods, each pool-sized, tuned, and auto-scaled independently. An intelligent scheduler sits in front, directing each request to the right instances. The magic glue is the KV cache handoff. After prefill computes the cache for your prompt, a sidecar orchestrates a point-to-point transfer of those tensors to a decode server over fast interconnects. Your prompt gets read by one specialist and answered by another. Disaggregation only works if shipping the KV cache between machines is nearly free, otherwise the transfer eats the win. That is the job of NIXL, the NVIDIA Inference X4 library. NIXL provides a memory abstraction layer that spans CPU memory, GPU memory, and storage backends, and it moves KV cache tensors point to point using RDMA, Remote Direct Memory Access. So, a decode GPU can read the prefill GPU's memory directly, bypassing the operating system entirely. On AWS, NIXL's libfabric plugin writes the elastic fabric adapter for high-performance interconnect. In 2026, this is the standard transfer mechanism in both VLLM and NVIDIA Dynamo, which means the pattern is portable, not proprietary. Is it actually faster? AWS published the numbers. Their machine learning blog benchmarked llm-d's prefill decode disaggregation path against a standard VLLM deployment running tensor parallelism of 4. The disaggregated setup used 4 prefill pods feeding 1 decode pod, tested at 1024 input and output tokens, with concurrency climbing to 128 simultaneous requests. The result? Up to 70% more tokens per second as concurrency increases. And AWS ships a supported path, an llm-d container built with the EFR and libfabric libraries, integrated with Amazon EKS and SageMaker Hyperpod. This is not a research prototype, it is a deployable production pattern. The second thing the evidence shows is momentum. llm-d entered the CNCF sandbox with backing from Red Hat, Google Cloud, IBM Research, and NVIDIA, and its 2026 release train reads like a maturity checklist. Version 0.7 focused on production hardening and broader hardware compatibility. June brought posts on serving hybrid attention models at scale and on heterogeneous serving across 3 different GPU vendors in one cluster. The team's June deep dive on networking makes the key point explicit. Once you disaggregate, the network carrying your KV cache becomes the critical path, which is exactly why the RDMA plumbing from slide 4 matters. The ecosystem is converging on disaggregation as the default shape of serious LLM serving. Let's summarize. First, stop thinking of LLM inference as one workload. Prefill is compute hungry, decode is bandwidth hungry, and co-locating them wastes whichever resource your traffic doesn't stress. Second, disaggregation pays most when prompts are long or concurrency is high. That is where AWS measured up to 70% more throughput. Third, run prefill and decode as separate pools and let each scale on its own signal, exactly as llm-d does on Kubernetes. And fourth, remember the new tags, The KV cache now crosses the network, so RDMA class interconnect is part of your serving budget, not an optional extra. Split the brain, and each half finally runs at full speed. Thanks for watching.